Hey y'all. Today we're going to be looking at different ways to classify chemical reactions. By being able to classify them, it makes it a lot easier to predict them and to really understand what's going on in a particular chemical reaction simply by looking at its chemical equation. Okay, so the different types that we have. All right. Basically, there's two ways of classifying it. One is by the particles that are exchanged or transferred. The other is by the bonding patterns that are displayed when the atoms are rearranged. Now, two examples of reaction types based upon particle exchange. One of them is called an oxidation reduction or redox reaction. In this, basically it's a type of chemical reaction that involves the transfer of electrons between two different species. And all ionic bonds and many covalent bonds are formed through redox reactions. Okay. Remember, ionic bonds, definitely you're thinking, okay, yeah, for sure, something's going to get exchanged. Metals are going to lose electrons, non-metals gain electrons. That makes sense. But a little bit more complex is that many covalent bonds also can be considered, even though they're sharing, there could be considered a transfer of sorts of electrons if you are forming a polar covalent bond. So even though it's not a complete transfer, there's still a motion of electrons. Like if hydrogen and oxygen are bonding together, yes, they're sharing, but because oxygen is so electronegative, it's going to want to grab those electrons, and therefore it is transferring them, I guess, from the hydrogen to the oxygen. Even though they're still sharing, there's a bit of a transfer going on, so it can be considered a redox reaction. Now, another example that hopefully we'll get a chance to get to later in the year are acid-base reactions. Whenever an acid reacts with a base, it involves the transfer of hydrogen ions. In other words, a proton. Since a hydrogen atoms are made up of one proton and one electron. To make an ion out of it, if you take away the electron, you just have a proton. And so an acid-base reaction is often thought of as just a proton transfer, when one substance gives up a proton to another. Okay, as far as a hydrogen ion. And great examples between vinegar and baking soda, where you would have vinegar, which is acetic acid, up in the top or the left there, reacting with sodium bicarbonate. And those two will end up being still in solution, but baking soda will accept a proton and it's a base, whereas the acid gives up a proton, which means that it is an acid, okay, the vinegar. And you end up forming water. Every time you have an acid-base reaction, water will form as a product. And oftentimes, especially when you have a bicarbonate or a carbonate, CO3, you're going to end up with carbon dioxide gas. This is why, by the way, baking soda and vinegar produces all those bubbles. Okay, very important reaction. It's good for making cookies and pancakes and all that good stuff. Now, there are 5 types of chemical reactions based upon the bonding pattern that occurs. Okay, it's supposed to be that occurs. First of all, there are combination reactions. A combination reaction is in which 2 or more substances combine to form a single new substance. All right. So you have one pure substance, another pure substance. They come together and form a third pure substance, some sort of compound. For example, sodium metal reacting with chlorine gas will produce sodium chloride. So A plus B gives you AB. Or you could have 2 compounds combining together, such as calcium oxide and water. Those combine together to produce calcium hydroxide. Again, one substance here, 2 substances as reactants. Now, a decomposition reaction is the exact opposite. It's where you start off with one larger substance and it breaks down to two or more smaller ones, okay? Smaller or simpler substances. So here you have AB breaking down into A and B. For example, mercury 2 oxide can break down into just mercury and oxygen, okay? And you also have hydrogen carbonate that can break down into carbon dioxide and water. Again, one substance breaking down into two or more. Now, a little bit more complicated are single replacement reactions. Now, this is a reaction in which an element replaces a similar element in a compound. And in this case, you have basically element A is going to react with the compound BC. And if you notice, the A is going to take the place of the B. So the B is now a lone element, and A is now bound with C. Now, you could also, instead of replacing the first element, you could replace the second one, okay, like the anion in the compound. So here you have element Y is going to replace Z. And at the end, Y is now bound with X, and Z is all by itself. Either way, it's still a single replacement reaction. All right, example the first, you have magnesium that replaces copper in copper nitrate. So now you end up with magnesium nitrate in ionic form or in compound form, and you have the pure element copper. Along the same lines, the second example, you have chlorine that replaces bromide. So in the sodium bromide. So now you have chlorine bound with sodium, and bromine is all by itself. Now, there's the question, how can you tell if element A will replace element B, or element Y, how do you know it's going to replace element Z? Does it always replace it? And the answer is no, because if you look over here, these guys are together. Why doesn't copper just turn around and replace magnesium? All right. And to figure that out, there's something known as the activity series. You see, activity series is a list of elements in a decreasing order of their reactivity. And basically means that elements higher on the list will replace those lower in a single replacement reaction. All right. Whereas those lower won't. All right. Lower ones will not replace higher ones, but higher ones will replace lower ones. And this can be used to predict if a reaction will occur. Now, there are two separate lists, one for metals. In other words, for the purple one up here, it follows this pattern. Will metal A replace metal B? Or there's also one for nonmetals, like in the case of the green example here. Will nonmetal Y replace nonmetal Z? All right. So you have here, for example, if the lone metal is sodium and the compound contains zinc, since sodium is higher than zinc, then yes, sodium will replace it and the reaction will occur. However, if it's zinc all by itself and sodium's part of the compound, then no, it will not. Okay? No, it will not. And then here we have the non-metal. Here we say because sometimes oxygen, will it react all on its own with oxygen? In other words, will it corrode or rust? And we notice all of these guys will, including silver and copper, those guys will form oxides, but gold and platinum will not. So gold and platinum never rust or corrode. Here it talks about, will it react with dilute acids? So not all metals react readily with acids. For example, copper will not, and so forth. And by the way, if you notice, hydrogen and carbon, even though they're not metals, are still part of this list, because sometimes in weird situations, they play the role of the metal and are the first element in the compound. These substances will react with water. All right, everything from here up will react with water. Okay. Now, the other thing is here, this is the non-metal activity series. So these are the common things. Basically, fluorine will replace anything. All right. But bromine, if bromine's by itself, it won't replace fluorine, chlorine, oxygen, or hydroxide, but it will replace iodine and so forth. All right. Now, I want to show you just some brief examples of some problems that you might come across dealing with activity series, being able to predict, will a chemical reaction actually occur? So, for example, we have this guy right here, where perhaps tin, solid tin, might replace sodium in sodium chloride to produce tin 2 chloride and sodium metal. However, when we're looking at the activity series here, we look and we see, well, here's tin, and however, sodium is way up here, which means since tin is below sodium, this reaction does not occur, okay? Does not occur, cannot happen, it is impossible. However, looking at this possibility here, what about tin possibly replacing copper? Well, since tin is higher on the list than copper, then we say, yes, it can occur, and we would go ahead and try to balance it. And we have Cu, we have Cl, we have 1, 1, 2, we have 1, 1, 2. Hey, look, it's already balanced. All right, so this guy would occur. That's a good equation. All right, and we do the same thing here. Well, does chlorine replace fluoride, all right, fluorine in sodium fluoride? Well, looking at this, you see that chlorine is below fluorine, so no, it doesn't. This does not occur. We cross it out or whatever, that is not possible. But here, since chlorine is above bromine, see chlorine's here, bromine's down here, this one will occur, and we can go ahead and do the balancing. We have 1, 2, 1, we have 1, 1, 2, and we go ahead and balance it. We put a 2 in front of the sodium chloride, that makes that a 2, and the sodium a 2. And we do the same thing here. We put a 2 in front of the sodium bromide to balance out the sodiums. That makes that a 2 and that a 2. And now it's balanced. Yay. So this one can occur. So just a couple of examples for you so you can do these problems if you need to. Now, the next type is called a double replacement reaction. Now, double replacement reaction is like a single replacement, but instead of having a singleton element and a compound, here we have two compounds. It's a reaction in which basically the compounds swap partners, as it were, where the positive and negative ions of two separate ionic compounds exchange places to form two new compounds. So here you have the compound AB and CD. So basically A and C switch. And you end up with C now reacting with B and A now reacting with D. Now this generally occurs between substances in aqueous solution. All right, remember, I talked about this before. If you have just two ionic compounds that are solids, they're not going to be able to react very well together. But if you dissolve them in water, then they can. And when they're in aqueous solution, if a double replacement reaction, takes place, that's when you can tell, because usually either a solid precipitate forms, okay, a gas forms, it comes out of solution, or a molecular compound such as water forms. All right. So remember, precipitate's a solid product that forms from a reaction and settles out of a liquid mixture. So one example is this. Here we have potassium iodide, aqueous solution, with lead 2 nitrate, also an aqueous solution. And when you mix them together, lead 2 iodide, notice the solid. That's what indicates that it's a precipitate. This will settle out a solution. This will stay in solution. You won't notice any difference with this, but this will precipitate out, and boom, that's how you can tell a reaction occurs. Another example is this, where you have sodium sulfide reacting with hydrochloric acid, and it produces hydrogen sulfide gas. All right. And if you notice here, the hydrogen sulfide gas, it's a gas, it comes on out, boom, you can tell a reaction has taken place, even though the sodium chloride remains in solution. And another example, when we talked earlier about acid-base reactions, well, acid-base reactions can be considered also, looking at it from this point of view, can be considered double replacement reactions. Like you have sodium hydroxide reacting with hydrochloric acid. And if you notice, the H here will go and replace the Na here, and it'll become HOH. In other words, water, H2O. And then the Na will then be bound up with the NaCl, with the Cl to form NaCl, sodium chloride, table salt. But since it's an aqueous solution, it's basically salt water, and you produce even more water. Okay? And the last type is known as a combustion reaction. Now, when we talked about balancing equations, we talked a little bit about these. It is a reaction in which a substance reacts with oxygen gas, releasing energy in the form of both light and heat. Now, some can also be considered combination reactions. Now, a true combustion, this is a little tricky here. Basically, some textbooks classify any type of rapid oxidation where there's a flame to be combustion. So like if you have magnesium, remember we burned some magnesium in the Fired Up demo. When we burned the magnesium, it reacted with oxygen and poof, made magnesium oxide. However, some other textbooks consider true combustion has to occur only with a hydrocarbon, something that contains both carbon and hydrogen, like the burning of methane that I showed you. That was the balloon exploding, if you remember way back when. All right, so here we have hydrogen burning in oxygen to produce water. Now, this is an example of the first type, where it doesn't have a hydrocarbon, but it's still burning, it's rapid, and it produces, this is like a combination reaction, produces a single compound. Most do involve hydrocarbons reacting with O2, and these produce CO2 gas and water vapor. Remember, hydrocarbons are compounds made up solely of carbon and hydrogen atoms. A good example is this. This is propane. If you have a propane tank or go camping with a propane stove, this is the balanced chemical equation for that reaction. Notice how it burns in oxygen, and it always produces two things, carbon dioxide and water. And it's this which is a main problem that we're having with global climate change. Because every time we burn something, and we love burning hydrocarbons, we burn coal, we burn gasoline, we burn natural gas, anything, even if it looks like it's clean burning, all right, and doesn't have other pollutants, it's still going to have carbon dioxide. And that's still going to be a greenhouse gas, and it's still going to cause the overall temperature of the planet to continue to increase, much to our destruction. Not to be too dramatic about it, but yeah. So this is a problem. Every time you burn a hydrocarbon, it's always going to produce CO2. Nothing we can do about that. All right? And that is that. All right? And if you have any questions, please make sure you come to tutorial. Thank you.